quantum computing. Pavel has a long career in quantum science. He did a lot of experiments in a lot of European centers. I will only say that he started with quantum optics and trapped ion quantum computing at Innsbruck and ended up with superconducting quantum computing at Jülich, and he will tell us sort of the story of their project where I think they're trying to build an actual quantum computer in a non-industrial, non-commercial environment. They publish not in Science and Nature, but in the Spiegel.
We don't publish in Nature, we publish in normal journals.
So welcome, Pavel.
Yeah, thank you, Volodya. Thank you for invitation and for hosting me. Good afternoon, everyone. So we'll have basically rather a review talk. I will, of course, explain what we have done in Jülich and why actually our experiment was placed on the Spiegel journal. But consider this as my talk as rather my personal opinion about the field and where it goes and what are obstacles and what we can do and how can we scale up. Yeah. So I'm from the Institute of Functional Quantum Systems, and our group consists of approximately 18 people. We have one postdoc, 3 permanent scientists, and a bunch of PhD students, and a couple of master students, and all people are involved in different experiments. Interesting enough, we formally belong to the Jülich. Yes, and I suppose you're in Switzerland. You can talk German, and we're located in Germany. Also, here's Aachen, but we're located in Aachen, close to Jülich. So this is our new building where we have a labs and office space. And so you initially make a zoom out. So this is our building, and another zoom out. We have a lab there. And today I'm actually here. Yes. So we have to just fly to the south, and we arrive to the beautiful Lausanne. So this is our experimental research infrastructure. We have 2 experimental sites, one in Jülich, one in Aachen. We have 12 cryostats of different sizes. Yes, it's approximately 1 PhD student per cryostat. It's really luxury. And many years ago it was not available. So we have a quantum computing and control electronics. We have a microwave engineering and analysis. We have all desired equipment, what you could imagine, including network analyzers up to millimeter wave band. So we also have a fabrication facilities. We have very good clean room in Helmholtz nano facility in Jülich. We have 2 E-beam EBPG systems, 2 placis evaporators, etching, wet chemistry, dicing, bond inspection, 3D integration. Again, we have everything what we need, even more. Funding is, we have a core funding from Forschungs in Jülich, but of course it doesn't cover all our appetite. As you see, we have 12 cryostats and other stuff. We have many grants from the Federal Ministry of Research, Technology and Space. 5 projects altogether: QSOLID, GECOS, TAXI, LabQT, and ML4Q. And funded also some projects from European Union, like Open SuperQ. And overall, we acquired more than 30 million, definitely. So it's basically like, a bit boasting slides, yes, and here's outline for today. I will talk about quantum computing, couple of slides, what is it, application and required resources. Then I will explain some, pretty sure not all people can deal with superconductivity and understand what transmon qubit is. I will tell that. Explain why do we need another 10 qubit systems. Also talk about the quantum error correction measurements and our responses to challenge, and our conservative scaling message. So what is quantum computing? Quantum computing deals with an exponentially large phase space. Yeah? How to actually explain this? So we are dealing with the quantum data. And the quantum data is, of course, between 0 and 1. Yeah? So it's not classical. So now we have a qubit, which is closed here. And if you have just a single qubit, so for example, one qubit processor made in Forschungs in Munich in our lab, so we have two quantum states. Yeah? So if you take a 10 qubit processor made in Munich, then we have two quantum states in power 10. So it's really 10 to the 24 quantum states. Of course, we are dreaming of 8 qubits, which is 64 qubits. Yeah? Then actually the number of quantum states is 10 to the 19. It's 10 to the 20 is 64. And compared to the cloud storage total available in the world is 2 to the power of 60, and atom in the universe is 2 to the power 270. So more qubits you have, apparently larger Hilbert space you have. What you do with this Hilbert space? Okay, initially you always start with all qubits prepared in state 0, right? So you can write a quantum state, and then you start to do any operation on a single qubit. But since you're dealing with a entangled state, you involve all the system in the rotations. Yeah. So basically, you do one step in quantum computing, but this step in quantum computing is just one operation. But try to make it a quantum in the classical computer. If you deal already with a number of qubits exceeding 20. Okay. What kind of applications of quantum computer? So one of the current applications was cryptography. Yeah, so that was people were screaming, and all cryptography is based on the factorization of integers. And of course, there was kind of like estimation of how much resources do we need. Okay, let's say you want to factor a 2048-bit RSA integer, and in 8 hours, and it will require 20 million noisy qubits. Right, so compare with the number of qubits which we are dealing now, it's completely insane. Right, now it was, recently was another article, you don't need maybe 20 million, you need actually 1 million qubits, yeah, but still, it's a lot. Maybe in 2035, maybe it will be 100K, but still is a lot. Another application landscape, yeah, so you can do optimization, different optimization, you can deal with the finances. There was an article, also not in Nature, not in Science, in some glossy journal, that one of the banks demonstrate quantum-enabled algorithmic trading with IBM quantum computer. I don't know, I was trying to understand what's going on, but all information was somehow not available. Yes, there was another more interesting article, application of quantum algorithm for the risk analysis in business. So you need approximately 20 error-corrected qubits, right? So it's a bit better. It's not talking about thousands or millions. It's more kind of reasonable, and it's kind of even seems to be feasible. The more interesting is actually if you look at quantum chemistry, yeah, because if you do something clever, you have to work with 30 or 200 qubits, and you can do hard-to-fork calculations on the quantum computer. So then actually I will show you now very roughly how to deal with that. Suppose you want to you want to drink a good cup of coffee, right? And here's an example of the caffeine molecule. It's purely organic, and if you want to simulate, you have to write molecular Hamiltonian in coordinate representation. So it's very complicated, therefore actually, please don't look at this, look at the colors. Yeah? So we have nuclear kinetic energy, electron kinetic energy, electron-nucleus interaction, all interaction included, and you have to do something with that, and it's a bit complicated. And we need to massage this Hamiltonian and to prepare it for the quantum computer. What you do initially? So, you rewrite initially in the so-called second quantization term. Yeah? So basically, you write in terms of the creation and the destruction electrons in certain orbitals. Yeah? Because of electrons in a molecule, they sit in certain orbitals, and you can add or destroy electrons. Yeah? All these coefficients can be calculated, so you just ask your good friend, and a good friend must be a theoretical theorist, molecular theorist, and he can calculate all these coefficients easily. And next job is actually, because of still, quantum computer doesn't understand all these operators, yes? What you do, you perform so-called Jordan-Wigner transformation. So you write Hamiltonian in Pauli strings. Yes. So all these operations will be actually strings of different Pauli matrices. X1, for example, here Z2. It could be very long. And then you use a so-called algorithm of rational quantum eigensolver, where each Pauli term, all the strings, must be calculated. Yeah. It was many times demonstrated, was many articles. So here's, for example, the demonstration published 10 years ago approximately, energy versus bond length for the hydrogen molecule. Yeah? So you have a theory, and then actually you have experimental calculations. Red one corresponds to exactly algorithm which I explained. So there was, yes, this is exactly this article. Look, you write full Hamiltonian in terms of different operators. Yeah? So every operator is a Pauli matrix, and you have to calculate step by step every Pauli string and calculate the energy levels. So resources required for the quantum chemistry. How much we need? Here's actually on the left hand side you see the example of molecules: hydrogen, lithium hydrogen, then iron cluster, then the caffeine, and you have spin orbitals and spin orbitals associated with number of qubits required. Yes, and for example, for caffeine, a number of Pauli strings is between 10 to the 4, 10,000 and 1 million. It's a lot. Yeah, one orbital, one qubit. So you have to calculate 10 to the 6 Pauli strings. This is a lot, and you have to repeat, and average. When you start to understand actually how much really we need, yes, and then you start to think, okay, what kind of task can you do it? Yeah? So if you do simple simulations with a variational quantum eigensolver, you need approximately number of qubits 50, 100 logic operations per Pauli string. Error for the single qubit operation 10 minus 5, and error for the 2 qubit gates 10 minus 4. This is it's barely attainable with any quantum computing platform right now. Yes, even simple calculation. But if you want to do something more serious, you need already 200 qubits, 10,000 gates, 10 minus 6 single qubit gate, and 10 minus 5 qubit gate. Yes. So this is where we have to go, and without quantum correction, this will not be achievable, unfortunately. Let's have a look what kind of quantum platform we have. Yeah? So here's 4 examples. We have trapped ions, we have atoms, we have spin qubits, and we have superconducting systems. Yes, and the people now screaming about atoms. Yeah? But what is bad about atoms? I mean, okay, you can of course trap many atoms. You can trap 1,000 atoms. You can maybe even control them. Coherence time is excellent. It's seconds. 1 qubit gate is pretty fast compared to the coherence time. But readout is quite long, yeah? So it's milliseconds, and readout error is large. And the circuit depth is approximately 100 still, limited. Okay, trapped ions. Trapped ions, to my taste, is of course much more developed platform. So you can work with many qubits, you can control them pretty well. A single qubit error is 10 minus 5 level, and there are even reports you can reduce it to 10 minus 7 level. 2 qubit gate is 0.1% is still good. You can make a good readout, and circuit depth is pretty large. But look, it's actually we're dealing with the microseconds. Yeah, 1 qubit gate is 10 microseconds. 2 qubit gate is 100 microseconds. It's a simply very slow system. Yeah? Therefore, actually, when people start to ask, okay, Pavel, why you do superconducting qubits? Well, because I was working here with trapped ions, and now I'm decided to switch to the dark side. So, but the points actually require algorithmic depth. It will be the same like with the ions, but we also have to take care about the pace. How fast can you make calculations? And superconducting are much faster. It's nanoseconds because the speed of light simply 10 to the 6 times larger compared to the speed of sound. Yeah? Because if you have a string of ions, so you have a phononic interaction. Yeah? So you have to take care about phonons. And the speed of phonons is much less. Okay, so that's why we prefer. Well, this is how we argue, how we sell to the external world why superconducting qubits are interesting. Yes, quantum computing. Yeah? So this is a picture of our lab, and the quantum computing has, of course, many interesting facets here. And the main facet is, of course, how to design quantum circuit. Yeah? So this is a picture of the 1 qubit processor. Here's a picture of the 10 qubit processor. Here's the cryostats. We have to make a design. We have to understand how to make a fab. And fabrication is extremely important. It's actually a 60% of success, if not more, actually. So without good fab, you can forget about the good experiments in condensed matter physics like we do. We have to take about packaging. We have to take about care of RF engineering, microwave engineering. We also can work on amplification, novel coherent materials, and it's again the same issue: fabrication, cryogenics, RF engineering. Another one which I don't want to cover, but is important, software programming. Yeah, because of you have to control many qubits, calibrate them, and actually, if you look on the normal day, most of our people writing Python codes in an actual experiment. Right, so our group is dealing with all interesting facets. So this is how Tuesday look in our lab. So Dima and Harsh are installing experiment here. So here's a qubit, here's actually the magnetic shielding box, filters, and a big cryostat. And usually we cool down Friday, and on Monday everything is cold, yes. So this is Wednesday in our lab, and here's Mark and Marcello working on development of the parametric amplifiers and investigating different materials. So, all right. So, yes, we're dealing actually with superconducting qubits, and superconducting qubit is nothing else as electrical circuit. It's simple electrical circuit. Yes, and then actually the major question: when electrical circuit behaves quantum mechanical. Yes, and of course you need this wonderful machine, which is called dilution refrigerator, and you have to cool it down. But still, what is this electrical circuit and how to make qubit out of this? So here I show a couple of slides about quantum circuits and resonator. Here's an example of the standard chip, aluminum thin film, 50 millimeters on silicon substrate. And yes, we see kind of like this wiggled line is usually resonators. And this process, this is non-linear resonator. Yes. And here I want to explain what's going on. We start from the basics. Yeah, so this is bricks of contemporary civilizations. So it's, of course, it's iPhones and mobile phones, computers. And if you look inside, we are dealing with resistors, we are dealing with inductors, we are dealing with capacitors. You crank up the frequency, you go to the microwave frequency range, And instead of resistances, you deal with impedances for every element. Okay? Yeah, now the question is actually, do we need the soldering iron? Do we need soldering iron for that? Yeah, I was always wanted to build a qubit with a soldering iron, and I still want to do it. It's not my dream. I don't know how to do it, but I wish to. You know? All right. How to? Well, first of all, we deal with a simple sterilization. So we couple in parallel capacitor and inductor. This is harmonic oscillator. Yes, and every theorist, if you ask him how to deal with that, and he will reply to you, okay guys, you have to start with the basics, you have to write down Hamiltonian. Hamiltonian is simple. It's nothing else as electrical and magnetic energy, electrical energy associated with capacitance, and magnetic energy associated with inductance. Yeah? So you have a current converted to the voltage of the capacitor, and you have oscillation. You have equidistant levels. What you do, you put actually, this the tilde signs, you start to work with the canonical operators. Canonical operators have such commutation rules. And then actually you find out that, look, everything is quadratical. You deal with a quadratic Hamiltonian, which yield you equidistant energy levels. Right? So simple. Interesting enough, okay, you plot, now here you see the plot of energy versus current voltage. Yes. And here's actually different colors are plot wave function for the different state. Ground state, first excited state, second, 2 photons, 3 photons, 4 photons. All right, interesting enough, well, all wave functions are symmetrical. If they're symmetrical, then the average amplitude is 0. But however, squared, yes, so the noise, the fluctuations of the every operator is not 0. Basically, circuit fluctuates. It's kind of, suppose you have a bell, bell is also resonator. Yes, and this bell always ring, even if it's ground state, always ring. Yeah, so this is a simple quantum device, what we do. Now, you want to really deal with the quantum mechanics, fine. You have to make resonator, which is well decoupled from the environment. Q, the quality factor, has to be extremely good. In the state of the art, usually it's 10 to the 4, 10 to the 7 in good labs. Yes, the bad labs is actually less. Yes, we need, of course, low temperatures. So since you are dealing with a quantum, so the thermal energy must be less than the energy of the quantum. And for 5 gigahertz, it implies the temperature must be much less than 0.25 Kelvin. Therefore, we use this dilution refrigerator which cool down to the millikelvin temperature range. Yeah. All right, so how to estimate how much noise, voltage noise you have? Simple. Charge energy is equals half a quantum. You do calculation, you get 1 microvolt. Okay, you cannot actually fill it with a tank, yeah, like a battery. But it's reasonably high signal, which you can sense. All right, resonator is boring, yeah, because resonator has an equidistant level, and we need to make some kind of, we have to select 2 levels. Here or there doesn't matter, actually, yes. And how to do it? Okay, we have to open up potential. And then, of course, you start to change the distance between levels, and you make it a bit non-linear. So we need non-linearity. So here's an example how we do non-linearity. So we can actually forget about the second one. You can do it with a single. So this cross is actually a Johnson junction. What it represents? So if you start to zoom in, so you have basically the so-called transmont qubit. So you zoom in, you have a squid loop, so-called squid loop. But again, you can do it only with a half. And you zoom in again, and you see actually you have a Johnson junction somewhat here, yeah, when actually 2 orthogonal paths overlap each other. So it's a Johnson junction is a transition between 2 superconductors. So you have superconductor, then you have isolator and superconductor. again, yes, and remarkably supercurrent can tunnel through it. It's interesting stuff. And this Josephson junction behaves like a nonlinear inductance. And then actually you can calculate all parameters for the junction, what you need, resonance frequency usually between 3 and 9 gigahertz. Non-linearity for this transmode qubit is unfortunately a bit small, is between 2 and 300 megahertz. But however, you still can select 2 levels easily for the computational subspace. And the control for this qubit is nothing else as a microwave electrical signals. So simple. And so difficult, yes. Yes, and now currently Transmon is a workhorse for the most of superconducting platforms, yeah, including a flagship IBM, Google, Rigetti, IQM, we're dealing with the Transmons, and also surprised that your lab is also dealing with Transmons, interesting enough, yes. Why? Because Transmon has a high coherence, yes. It's very simple design, very simple to fab. However, there are of course drawbacks because of there is no such things like a free lunch, although I get today. Yeah. But there is a weak unharmonicity, there is a leakage associated, and you need to make careful frequency planning if you start to build something scalable. All right, and then actually you can ask me, okay, why do you need actually 10 qubit superconducting demonstrator? IBM has 100 approximately, Google has 100, IQM 20 or 50, nobody knows. Secret information, yes, and other guys, look. We started in 2024, yes, and what you do, you initially make so-called pilot devices. You understand whether qubit design is good, whether fab processes are also good. So you learn fab processes, you make readout, you work on coherence, then you make 5 qubit device, yes, you work on architecture, gates, fidelity, you can couple 2 qubits and see what happened. Then currently we are here, we have a 10 qubit processor, here's a picture of our processor. I cannot actually show you all details because of recently I realized that European Union started to protect quantum technology, and we are at the level of 5, meaning actually I cannot show everything on details and I should not tell all parameters of the circuit, e.g. EC. This is dangerous already.
Even if your gate fidelity is bad?
Even if the gate fidelity, especially if the gate fidelity is bad, yes. Yeah, so then actually you have to keep under secret, yes, secret information. Right, but suppose you have a 10 qubit device, what you do? Okay, all right. So you have to learn how to control. You have to learn how to calibrate. You have to understand fabrication process, yield, especially yield and quality. Because if every qubit behaves differently, every chip behaves differently, come on, how long it will take you to calibrate and understand what's going on? So then actually you scale up to 2030, it's, I think in 2 years we will be there. You start thinking about how to scale, how to make algorithm, how to make automation, how to make multiplexing readout, and start to deal. Basically you start, I show you the path towards larger circuits, and this path will teach you how to deal with the large circuits, how to experiment with them. Okay. So here I'm proud to show our 10 qubit device developed in Jülich, fabricated in Jülich, a linear chain of 10 qubits, 10 tunable transmons plus 9 tunable couplers, material aluminum, no surprises, readout multiplexing 5 qubits per line. All right. So this is a topology of the circuit. So we have 10 qubits, yeah, crosses are qubits, red dots are couplers. Why couplers? Because of coupler is actually, so you have a qubit QA and QB, and coupler is, depending where it sits, varies the coupling strength between these two. Yeah. What kind of gates we can realize is IC phase, complicated. I swap is less complicated, but still requires some job. So this is a 10 qubit device chip matrix, single qubit gate fidelity. So what I plot here is the population of the ground excited state versus number of Clifford gates. So what you do is you You perform 1,000 of elementary operations and see how your quantum state dies. Yeah, and then actually you can understand what happens with the fidelity. Yes, fidelity of course is not unity, and the population of course mix. So single qubit gate fidelity is 999. 2 qubit interaction for the iSwap is 999. Readout fidelity is approximately, well, it's usually more than 95%, it's now 97%. Yeah. However, all qubits are operational, but we can now, frankly speaking, we can work only with 2 now. Yeah. T1 is approximately 50 microseconds. We do have good chips where T1 exceeds 100 microseconds, but it's not so often.
What is your gate at?
Sorry? This iSwap. This is iSwap.
But how would it work?
So you tune a coupler in the probe, yes, and this is it actually, and then actually qubit aligned, and you actually also as a coupler is aligned. A coupler allows to interact with two qubits.
So you need to tune two qubits.
Yes,
one coupler
yes, exactly.
to the same frequency.
Yes, more or less, yeah.
And
So for the qubit T1, T2s, I was wondering with scaling from 0 to 10, does the T1 typically decrease because of the scaling up? And
Okay, so I would say we have not seen a really decrease of T1 or T2 when we started to increase the number of qubits, yeah, the circuit scale. So basically it means we understand what's going on. Of course, we have kind of add-on technologies. We have crossovers. Yeah? So we have also other interesting solutions. We understand. We carefully plan frequencies. Apparently, yes, and we have reasonable T1. It does not goes up. It doesn't go down substantially. So there are chips where T1 above 60 or 80 microseconds. We have this here, yes. So this is what we are currently, where we are currently. So we can make 2 qubits, iSwap, we can make single qubit gate, so we can read out, single shot readout. We have very good fabrication process. This is extremely important, all right? And next step is, of course, to do something useful. Yeah. Here I want to remind you quantum error correction, how does it work actually. So you have a two-dimensional circuit, yeah, where we have a yellow data qubits, and we have these blue ones is measure qubits, yes, and usually a single measure qubits is connected to the 4 data qubits in order to check them, yes. And the point is the following: if you start to measure what's going on with a single qubit, right, this population, you destroy the quantum state. If you especially measure operation sigma z or sigma x, sigma y, it doesn't matter, you kill it. What you do instead, you create a so-called stabilizer. Yes, so Z1, Z2, Z3, Z4. It's kind of sometimes it looks confusing, but what we do is actually we entangle initially with this qubit, with this qubit, with this qubit, and with this qubit, right? And we measure parity instead of population. If you measure parity, parity is operator which commutes whether sigma z or sigma x, meaning actually you don't destroy quantum state. This is how quantum error correction works. You do 4 CNOT gates. So we have a measurement of qubit, 4 CNOT gates, or 1, 2, 3, 4, and then you measure a qubit and you check basically what's going on, parity, yes? Meaning actually, if you calculate how many operations you need, measurement counts of approximately 10 to 20% of the total operations. So measurement is extremely important. Readout is extremely important. It's really worth to invest your attention to the, not only to the gates, yes, but also to the readout. All right, so here's actually examples of what you measure. So you measure syndrome, basically this is a stabilizer. So if you see the parity is destroyed, either you correct, either you understand where your errors occur, and you continuously observe errors appearing during operation of the algorithm. So, and my estimate is actually quantum computer is 95% busy with checking error syndromes and correcting them. It's basically kind of, you build a house, but house is actually falling apart, and you always have to repair it, yes? It's dealing with the checking with itself.
May I ask about how
Yes, please.
clear the blue and red, what color means?
Colors actually is different stabilizers. Blue is Z stabilizers, red is actually X, Y stabilizers, yes? Yes, basically this is what quantum computer does. You observe errors appears, and actually you have to notice where errors are, but 95% of algorithm is actually busy with the quantum error correction. All right, so therefore actually qubit measurement is very critical, yes, and currently readout is actually normal numbers, actually 1% is a readout error at half a microsecond time. Yeah, and 2 qubit gate error is actually only 0.1% at a 20 to 30 nanosecond. So if you have a bad readout, so basically readout is 10 times worse and 10 times longer. So therefore actually readout is extremely critical now. So we have to focus on the readout. So a couple of words how readout works. Yeah, so it's basically, indeed, we are dealing with a Schrödinger cat. So here's actually, again, here's a simple circuit. You have a qubit. Qubit are connected to the resonator, and the resonator connected to the readout line. And this connection is extremely important, yes, and because of, we don't measure the frequency of the qubit itself. We measure the frequency of the resonator. So how it is realized is the following. Shortly, qubit is detuned away from the resonator in a so-called dispersive regime. Yes, and then actually what happens, I don't want to show this magic, but you have a so-called state-dependent phase shift of the readout signal depending on the qubit state. Yeah? So you have on the right-hand side, you have transmission, phase and magnitude, and you see that resonator has different frequencies for state 0 or 1, and state 0 or 1 correspond to the phase delay. Either you, for the state 0, you have, let's say, 0 phase delay, and for the state 1, you have simply minus. Frankly speaking, we are dealing somehow with the classical physics, yes? How to measure the phase of the signal efficiently and fastly. Before we go to that, again, actually, you want to understand, okay, what is the kind of physics and philosophy behind. Please recall so-called Stern-Gerlach experiment. Yeah? So we have a beam of atoms, and atoms has different spin, and then actually you split to the spin up, spin down. It's absolutely the same thing. Yeah? So basically, what we do, we split to basically the signal into two phases, either plus or minus. And the quantum measurement is nothing else as obtaining information about the system. Yes, and obtaining information costs energy and causes decoherence. Decoherence is nothing else as the loss of phase information in quantum state. If you have residual photons in the cavity, you have decoherence. Yes, even if you have a, thermal population, very small thermal population, 10 minus 2 photons in the resonator. The phasing associated with the thermal photons will be approximately 100 microseconds. Yeah? So it's quite a lot. Yeah, how to deal with it? Yes, so how to optimize readout? There are many different ways. Yes, there's approaches dealing with the hardware, and there's approach dealing with the signal processing. So the parent approach actually, okay, you want to make readout fast. How to do it? Okay, you do Purcell filter, which effectively kind of like a wide band resonator. You can read out quickly, but cavity reset is under question because if you always have stray photons after the readout. Scalability is under question because of Purcell filter. Is actually its space on the chip. Stray photons, okay, you have a resonator which is broad, yes, of course it will absorb everything. Right, how you deal here? Well, you actually proposed to work at a very high frequencies. Excellent. It's a fast readout because the float factor can be a bit less, but resonator will be well coupled. Qubit protection, you do it automatically without per-cell filter. Scalability, definitely because of smaller frequencies. Stray photons. Well, if you work at 20 gigahertz, you can forget about stray photons. No stray photons. Power, you can deal with that. However, you need parametric amplifiers, and this is not easy in this frequency range. It doesn't mean you cannot do it, but still, you need parametric amplifier. So another method is actually okay. We focus now on the cavity cleanup. Yeah, you send the readout pulse, and the resonator actually rings. Yes, we actually can construct such a pulse which actually cleans up the cavity automatically. Leakage is still under question. I don't know how to solve it yet. Yes. So a couple of slides how to do it. So it's 19th century science. You have a resonator, and its response of the resonator is described by the so-called Duhamel integral. Yeah? So many people here from France, and Duhamel was a mathematician, he was a mechanical guy, and he introduced the description of mechanical system via convolutions. All right. So even you apply kind of nice Gaussian pulse, you think everything is smooth, but still, resonator will ring. Yeah. So you pump. Here's upload intercavity signal versus time. You pump up the power in the resonator, but then actually you will have very long decay. So this is what I mean. You need to clean the cavity. Readout, let's say, at 1 microsecond, but look, pulse is over, but resonator continues to ring. Very simple. So you have to wait a long time. What we propose instead, okay.
What's your kappa?
What's
the value of kappa here?
What is kappa here in this experiment? Is approximately 2 megahertz, if I'm not mistaken. Yes, it's very decoupled.
That's not bad.
It's not bad. You know, Valraf use I think 50 megahertz, even more, yeah, 70 even, yeah. We want to work with a kappa equals 5 megahertz. Yes, I think it's optimal. 3 to 5. Yes, we have below definitely. So again, this kind of like Duhamel formalism via response function, you can kind of like invert. Yeah, so let's say I want to have such a response function which doesn't decay so long. How to make it easily? So this is entire function is a desired response, and then you calculate back via response function the input, right? Input looks very interesting, yeah. So kind of like oscillation and this kind of stuff, right? But so at the end, actually, I plot here intercavity signal versus time. So 500 nanoseconds. So number of photons, okay, we pump to the critical number of photons, and then actually we drive back to 10 minus 2. We reset the cavity immediately. Yeah? We read out the cavity and immediately reset it. The silent fidelity is 99.6%. Yeah, this is what we can do. So another activity is for readout optimization. We are dealing with the niobium titanium nitride materials. This is so-called high kinetic conductive materials, and we can build parametric amplifiers. Currently is bandwidth 4 gigahertz, gain 15 dB.
Why the gain is so noisy?
This is ripples. This is because we have many reflections back and forth inside the metamaterial. Here you have electrical metamaterial. It's very difficult to match impedances, right? So you have kind of like every part of the circuit has different impedances, and you have reflections, and they are usually amplified.
If you're using this amplifier, is the IQ block also like just moving around? Can you really using this?
Yes, you can do it. Yes, so what? You have gain a bit higher or gain maybe a bit lower. So what's the problem? So we need actually, you have to measure the
If your gain fluctuates, your IQ block will fluctuate.
if pump fluctuates, and even if everything will fluctuate, but usually it's very stable.
I mean, like if you zoom in, like in the dispersive rate is 1 megahertz, like GME. And
You mean the size of the one wiggle?
Yes.
It's usually 10 megahertz.
Okay.
And with a pump, you can always choose. Of course, you can ask me, okay, right, if you have 10 qubits or let's say 20 qubits, right? So this might be the question, but I haven't seen any kind of, like a jitter bit on the IQ plot. I haven't seen it, even on a junction automatic amplifier. Neither on this. It's usually stable. But it's interesting, yeah. But we haven't seen it.
What kind of boost to signal to noise ratio does this amplifier?
This is a good question. I don't know yet. We haven't measured. We have not. So there are not many experiments with this kind of amplifiers. With match circuits. I want to also turn it to the connect to the 10 qubit device and measure and see where we will be.
Compression. What is compression?
What is compression?
Or
What is compression of amplifier? So suppose actually, so you build amplifier, right? And then actually you think, okay, I have a 40 dB gain or 20 dB gain, right? And it looks like it will deliver the same gain for all input powers, but that's not the case, right? Because at some point you start to saturate amplifier.
so my
It's basically when the gain start to go down. Yes.
at input or
Yes,
output.
at the input, yes, it's
Okay.
input power where the gain drops by 1 dB. Yeah, that's compression.
It's a high power, right?
It's very high power, yes. It's a lot. It's 10 nanovolts, by the way, which is a lot, yeah. All right, so now I start to kind of wrap up slowly, yeah. So system engineering change. Yeah, suppose you want to build a quantum computer which helps you to develop a very interesting caffeine which will actually kick you. And what you need for that? Yeah, so we need, let's say, 100 qubits, and the 100 qubits in our architecture presumes 190 couples. You need 500 control in the route lines. You need thousands of cables, filters, and other components. You need a lot of cryogenic space. You need electronics. You need for readout control. It's basically price, power, cooling, software to orchestrate such a machine. And the number of people currently is equals to number of qubits. I haven't seen exception. Even in optics, it's always like that. Yeah, you can even divide by a factor of 2. Number of people in a team, yeah? If not by 3. Google has 200. They have now 100 qubit device. Right? This is systems engineering challenge. Right? And you have a material challenge. You know, here's I plot the model of TLS. Yes, it's mainly for the people who deal with it. Yes, you have Johnson junction, and you have the different models for these TLSs. And the TLS's density for the transmon is between 1 and 10 per gigahertz. And here I plot spectroscopy of the qubits, so we measure T1. So T1 at different frequencies versus time. And these red lines showing where you don't want to park your qubit because of T1 is very bad. Yes. Basically what I want to say is TLS defects limit qubit coherence because of you have a strong frequency dependence. And sometimes you have, not sometimes, you always have slow temporal fluctuations. And when we do the gates, we shift all qubits simultaneously, and it's a complete nightmare where you have to park, such that we have to avoid interaction between the qubits, between neighbors. And it's really a nightmare.
Is it data reproducible if you just...
No, it's not reproducible. Sometimes, yes, okay, if you do it in 1 minute, yes. Maybe in 1 hour. Maybe, if the circuit is good. Yes?
Basically, the question is something strange in frequency.
Yeah.
Is it just a time fluctuation, or is it actually reproducible? So is it the frequency that's special, or is it the timestamp that corresponded to that?
You mean here, right? So, no, usually look, we definitely see fluctuators, but sometimes, okay, you see this guy, yes, kind of like wiggly, going to the right, left, and then disappears. Where it is, I don't know. Or another one, yes, you observed initially here, and then it jumped. There is
Okay.
even worse, appearing, disappearing, and make complete nightmare, yes? Right, a circuit architecture change, yes? So, apparently, our field demonstrated impressive scaling up to approximately 100 qubits. Yes, so we started, this is 2013 design, early 5 qubit transformer chip, and here's the 2025, 105 qubits in Google. But the point is actually, all this flagship platform, IBM, Google, Rigetti, IQM, they're dealing with the legacy design is the same transformer as it was invented in 2008, yes? And the same legacy ideas appears everywhere. We have a qubit design, we have the same fabrication. Nobody want to really pay attention inside fabrication because of people usually think in the team, right? Fabrication is kind of boring. It is engineering job. No, guys, it's not engineering job. First of all, it's really kind of, it's very scientific job. You have to understand what you're dealing. You make a material, you have to characterize, understand what's going on in the material. Secondly, suppose actually you don't have any capacity in your career to continue as a postdoc or professor. If you know that, you will always be in a good shape. Yeah, so many companies currently in Germany, they are really hungry for these people with the fab experience. Yeah? Right, so we have cryogenics, still all cryogenics, control, readout, everything is kind of like, our field relies on the same technology introduced 15 years ago, right? And of course, when people ask me, okay, when you have will you have 1,000 qubits? Come on, how to make it? It's we have only incremental progress based on a transformer. Right, so what I want to say is actually scaling quantum computers is not just number of qubits, yeah? So, well, you can deal with a single qubit, it's really difficult even with our big team deal with the 10 qubits, but if you have a number of qubits more than 100, it's more complicated, yes? And always about systems performance. It's always about qubit design, fab, so extremely important, and then actually gate, error software, and control redundancy comes also. So, our approach is the following. So here's actually upload algorithm success rate versus system size, number of qubits. Yeah? You know that actually you cannot make fidelity equals to 1, otherwise life will be too sweet, yes? So fidelity of the single qubit gate and 2 qubit gates limits the algorithm success rate. Let's say you have a fidelity equals 10 minus 3, 999, yeah? 999 fidelity is error is 10 minus 3. But come on, when you start to see what fidelity of total algorithm, it goes down pretty quickly. You cannot actually even entangle 100 qubit with such error. So you need much better. So you cannot just expand, make a brute force scaling without working on errors. Brute force scaling means errors accumulate, algorithm will be destroyed. Right, so we approximately somewhat here, and here's a different examples. So Google is here, so this is experiments in China. Key challenge, of course, qubit performance. Well, I think my feeling is actually all these companies and the flagship platforms, they want to go this way. You basically increase number of qubits because of investors requires that. But instead of that, we want to work on the qubit performance. So phase 1 is actually our goal for the 2027, and then slowly we go to reach quantum error correction quality. Yeah. So basically today's, yes, you can ask when will useful quantum computers appear. Okay, all right. Today we are approximately in this area. We cannot do anything useful. We cannot do anything useful, so we need to create a quantum error correction, long-lived qubit. However, we can make very interesting demonstration. Maybe in 5-10 years, we can achieve quantum error correction with lambda equals 10. Yes, and definitely more than 10 years it will require to make large-scale fault-tolerant machines with application of quantum chemistry and finances. Right, and then actually we can make a very nice, we can create, so we can drink very nice coffee. So my time is up, and the take-home message: quantum algorithms, of course, require some efficiencies, right? You want to make something useful, you need 100 of qubits, not qubits, but error-corrected qubits, good qubits. And the current devices remain hardware limited, right? So we still rely on the legacy architecture. And the scaling requires better qubits and better architecture. And of course, everything moves towards quantum error correction and fault-tolerant quantum computing. So with that, I thank you for your attention.
Right, we have a few minutes of questions.
So when you turn on the about to qubit gate, when you turn on the coupler,
Yes.
does the T1 and T2 qubits all coupler?
Yes, you have to be very careful, and everything has to be calibrated. Moreover, you have to take into account second neighbor, what it does, and you have to detune it. And even third neighbor, you have to also detune it, yes.
And
So
coherence, does coherence change a lot or not?
I wouldn't say it changes a lot, but it influences, of course. Right? Because of its electrical circuit, you have capacitive coupling, and you have to make careful frequency planning. Therefore, we always make calibration where all qubits has to be placed in which operation. Which is, therefore, actually, yes, and we are still struggling with the 2 qubit, and not with the 10.
And is there like why capacitor? No, why the coupler looks smaller than qubit in your schematic?
It is actually small because of it's a kind of it's a transmon for the high. It's a transmon, but this transmon actually sits can be tuned at a higher frequencies, slightly higher.
Other questions?
Yeah, so for the scaling, I mean, because in the layout you showed it, you had this kind of one-dimensional, like an array structure. I think with the 10 qubits. Yeah.
Yeah, this one.
Yes. So I mean, is this with this exact designs that you have? Is it possible to have two-dimensional?
Yes, but this is much simpler to realize, yeah, because if you want to have two-dimensional, you have to actually, you need a 3D integration.
Yeah, that's exactly.
Yes,
so.
exactly.
Yeah.
So, and, since we have only 15 people in the group, we cannot, so we cannot realize all what we want in terms of fabrication.
Yeah, but when you start to scale to a very large number, you're gonna, I guess, then the only option now is to just
Yes,
stick
of
to the
course.
1D.
Yes, this one, of course, with this one, still you can actually make many interesting simulations with that one. Yeah, scientific simulation, like how's called as actually Hubbard model for electrons, yeah, and maybe for magnetic chains. But for the something useful, you need actually a quantum error correction topology, meaning actually you need a two-dimensional grid. No way out. So then for that you need a 2D integration or 3D integration.
So at very last, I have a comment that basically all the technology we're using right now is based on the technology which I used like 10 years ago. But then it's like
20
years, 2013, by the transmon. But then you claim like there might be something really useful in next 10 years. But I was wondering if this architecture is not changing, how can we reach this?
No, it's not. This is how we sell, right, to the grant committees and to the government. But I don't believe actually we can. So here actually show. Yes, this one. Yes,
Yes.
like this.
If
I
nothing's
think
changing,
it's,
it's
yes,
just to the right.
we have to manage our expectation. Yes, it will be like this also, right? And let's say, okay, how many people can we hire? Maybe 30 qubits, yeah, Well, maybe we can reach 10 minus 3.
Aren't you worried it's going to go down like this? If you can't, that's another option.
Oh, this is another option also, yes. Yeah, but I'm optimistic, I have to show again. Yeah.
So either we have really good qubit, really low error rate, otherwise.
Yes, we maybe, yes. I don't want to say specifically, but we need another qubit architecture. Yeah, currently we have a transmon of fluxonium, right? But it looks like transmon is, well, so let's say you have a combustion engine, and you cannot fly to space using combustion engine. Yes.
Okay. Go ahead.
Are there any ideas to change the frequency range of your qubit, like to higher frequency?
Yes, we can go to the millimeter wave. Yes.
Yeah.
But the point is actually, first of all, its price is 10 times more expensive.
Yeah.
It initially scales linearly. Okay, if you go from 10 to 20, it's factor of 2. 20, 40 is factor 2.5. 40, 80 is factor of 4. It's more expensive. Then microwave losses are higher because of skin depth. Yes, of the materials, and then actually also dielectric losses. They scale as a frequency. Yeah.
And
Although you start to deal with other, of course, issues. Yeah. So you solve other problems, but millimeter wave is interesting but difficult.
And you were already using NDTI for your amplifiers, but are there
Yes.
any plans for using it on your transmon?
You mean junctionless qubit?
Junctionless or changing the pads to instead of
This is
aluminum?
actually, yeah, but then actually it's interesting. The point is actually, for the junctionless, actually, yes, we have a long discussion. I had long discussion with many people, and you need a material with a high kinetic inductance which has low loss. And this is very difficult to make because of high kinetic inductance is usually associated with a material that already have a high loss. Right? And it's kind of always difficult to match kind of like, high kinetic inductance and low loss. Yeah, so it's, they're reciprocally connected, unfortunately. So it's not easy either.
Right. Well, so Pavel, you're saying that if we have 30 million of money and all the equipment we can think of here, we still can build a quantum computer?
I don't think so.
Okay.
No, you can make very nice demonstration, let's say, but could not use for quantum computer. So I believe actually we have 30 millions. We can build very nice 30 qubit device here. Somewhat, let's say, okay, 30, somewhat here or maybe even there, right? To at least to show how quantum error correction will work. Yeah, for example, we need, let's say, 34 qubits or 35 qubits, basically 2 plaquettes for the surface code 17, yes? We can demonstrate how it will work, and will work nicely and say, okay, this will be scalable. But then actually we'll need 300 millions to scale it up.
This linear is number of qubits, the money?
Yes. It's here.
All right, well, let's thank the speaker.